Last but not least, we need to go to the last presentation that is titled Realistic 3D Simulation of a Hybrid Legged Wheeled Robot, and will be presented by Inês Soares. Inês, are you there?
Yes, I am. Thank you very much for the introduction. Okay, I believe you can hear me and see the presentation.
Perfect. Go.
Okay. Greetings, everyone. I'm Inês Soares from the Faculty of Engineering of the University of Porto. And as mentioned, I'll be presenting the paper Realistic 3D Simulation of Hybrid Legged Wheel Robot, co-authored with Vítor, Pinto, José, Lima, and Paulo, Costa. For the next few minutes, you'll thus not only hear about the simulation model we developed in the SimTwo simulator for the legged wheel robot we designed and built, but also about the robot itself. So first, I just want to emphasize that locomotion is a critical aspect in robotics, and hybrid locomotion systems have gained increased focus in research. Why? Because they are able to merge the strengths of each embedded mechanism and outperform their disadvantages. So when we think of combining legs and wheels, we can thus create a system with increased mobility and versatility, as we can align the efficiency of the wheels with the enhanced obstacle initiation capability of legs. Simulation is a crucial asset in robotics. The numerous variables of a system can be tuned, a variety of conditions and scenarios can be tested to assess the robot's performance, and realistic models will ensure successful operation in real-world environments. And all these can be performed while keeping the real vehicle undamaged. So I'll now start the description of our vehicle. The prototype build is shown in this picture, and the platform has been conceptualized to comply with three features: affordability, expansibility, and modularity. All these are key to guarantee that the architecture and structure of the robot is minimally affected by any additions or changes, that these are easy to perform, and that the robot's cost is minimally impacted. So the robot is a quadruped, and each leg has 3 degrees of freedom. The joints are equal in size and follow a circular configuration. So we have one rigid joint and two non-rigid joints. The rigid joint connects a limb to the robot's main body and rotates between minus 90 degrees and plus 90 degrees. And when we have this configuration, this leg configuration that combines rigid and non-rigid joints, the compliance of the leg is improved, as well as the robustness of the vehicle. Also, the elastic components of a non-rigid joint allow to accommodate impacts and floor irregularities, hence improving the obstacle negotiation capabilities and navigation in rough terrains. The limb includes wheels at foot end, which we have a rubber wheel, which is the driving wheel, and an omnidirectional wheel for stability and support. These wheels endow the robot with a low power configuration. All the joints and the wheel are actuated using brush DC motors with inline gearbox and built-in incremental encoder to determine the angular position. The motors use their own driver for motor control, and each leg has 3 Arduino Nano 33 IoT. Regarding control of the robot, each leg is controlled individually. PID controllers are used for position control of the hip joint and for speed control of the wheel. while state space controllers are applied to the non-rigid joints. The kinematic model of the robot was also developed, and it was considered that when in purely wheeled mode, we'll have the x-axis of the wheel aligned with the rotation axis of the hip joint. And so the variables used to derive the kinematic equations are represented in the figure, and the variables that we can control are the angle of the wheel, which determines the hip joint angle, theta, and the speed of the wheel, and they are computed using the equations on the left. The information on the parts that make up the developed robot was transported into the simulator. SimTwo is a robotic simulator with a 3D environment with incorporated dynamics, as it uses a physics engine, and so it allows realistic simulation of a variety of robots. The simulation model is shown in these pictures, and it follows the dimensions of the real robot. We have a main body size of
Inês, we cannot hear you. Can you hear me?
Can you hear me now?
Yes, Inês, go ahead, please.
Oh, I'm sorry. I don't know if what was the last part you heard.
I don't know if the problem was. Okay, go ahead.
I'll go ahead, yeah. So we have here the simulation model, which we decomposed the robot into a set of rigid bodies. So the leg links were modeled as cuboids, and they connect through cylindrical joints. Except for the joint for rotation of the omnidirectional wheel, all the others are actuated. And regarding
Inês, are you there? I think we lost the connection. Well, I think Inês. Okay, she's there again. You are muted.
Sorry.
Okay.
I'll share again, I believe.
Yes.
Okay. So I was talking about validation of the model. We used real data to compare it, to compare the response, and from the lowers obtained, we confirmed the realism of the model. Regarding the low-level control architecture that I've already mentioned, we implemented it in the simulator. The PID controllers were implemented using built-in functions, and the state space controllers were fully implemented in the SimTwo IDE. And we can see on the right the response of the non-rigid, the controller to a step change. The results are satisfactory, but there's still some refinement to be done in the parameters so that we can achieve lower overshoot values and shorter settling time. To allow control along the X and Y axis, we implemented the kinematic model into the simulation, and to observe the successful implementation, several values for VDN and omega were inputted, and we observed the legs and wheels positioning, so that we can, and you can see in these figures that the results correspond to what was expected. Therefore, the work developed focused on an innovative hybrid-legged wheel robot that we designed and built, and we also developed the simulation model, and the realism of this model was confirmed. To exploit the advantages of hybrid locomotion, we still need to improve the z-axis control of the robot so that we can develop and test algorithms for trajectory planning and obstacle avoidance, for example. To conclude, a special thanks to the authors of this paper, which were crucial for the success of this work. Also to the institutions we are part of, FIUP, IPB, and Inês. And thank you all for your attention. I'll gladly answer any questions you might have. Thank you.
Okay, thank you, Inês. Is there any question? No questions? Sorry, can you repeat the question? Or we cannot hear you. Can you please write the question on the chat? Okay, while Kirill is writing the question, I suppose.
Sorry. Oh, do you hear me?
Yes, perfect.
Yes.
Oh, so perfect. I want one question about Omni wheel support wheels. Why do you use support wheels? Why do you use support wheels?
Yes, thank you for your question. So the omnidirectional wheels are only used when the robot is performing on wheel mode. So it has the two wheels on the ground. And if we did not have the omnidirectional wheels, the robot would just fall as it would go to the lowest position. So that's why it's a support wheel. I think it answers the question.
Okay, thank you. Thank you for an interesting presentation.
Thank you.
Okay. Any other question? No? Okay, so thank you, Inês, for your presentation. And with this paper, we conclude this section. Let me thank all the presenters and all the people who were assisting for this session. And we will have another session at 9 UTC hour. So please go there, and thank you again for your presence, and good morning, and have or good afternoon for some of you, and hope to see you again. Thank you very much. Bye bye.